So welcome to the afternoon session. So our speakers this afternoon, so we'll have two speakers. The first one will be Damien Kerlioz from Paris-Saclay, who is going to tell us about toward energy efficient artificial intelligence with brain inspiration. So Damien unfortunately couldn't come in person because he is sick, and I'm very grateful to him have accepted to give the talk on Zoom from home. So if you have any question to Damien, then you can ask your question, and then I'll try to repeat so that he can actually hear the question and answer. And then the second speaker will be Julian, who is here, and at 3:30. Okay? And then we have a coffee break right after Julian's talk. Okay, so Damien, it's up to you.
Okay. Thank you so much for the introduction, and thank you for the invitation to talk at this really wonderful workshop. I really wish I could be here in person because the program is so nice. Also, an alumnus of this école, and I was quite excited to talk about my research in this room. So obviously, I did not plan to give this talk virtually, so I actually don't have my really good microphone. So please, if there is any technical issue, if you can't hear me very well at some point, please interrupt me, and I will do my best so that the presentation is clear. So yes, so the talk will be toward energy efficient artificial intelligence with brain inspiration. And my talks usually target more electrical engineering, physicists, or computer science people. And I know this time there will be plenty of neuroscientists in the room, which is very exciting. But I decided to keep my presentation the same way. This way also, if the way we talk about the brain is shocking, people can scream. But just let me a little introduce the motivations of my talk. So, I think everybody at this point has heard the incredible achievements of artificial intelligence in recent years. I think most of you have already seen this new AI by OpenAI, which is a language model that is actually quite amazing. Actually, I've been sick these past few days, and playing with it is most of what I have done. And in particular, I have asked it to write a poem about this workshop. So I basically only told it the title of the workshop, and this is what it produced. In the world of artificial intelligence, where machines and algorithms hold sway, the energetics of computation are the heart of what they do and say. In natural networks of the brain, where neurons fire and synapses spark, the energetics of computation drive the thought action of our heart. In both cases, the fundamental laws of physics and thermodynamics apply, and the transfer of energy information is the key to understanding why. So I was quite impressed. This is not the most beautiful poem that has ever been written. I mean, hardly rhymes, but the content, I mean, it really understood what the workshop is about. It understood what is specific about computer, is specific about the brain. It understood that the workshop is about the brain because that's not in the title. And it actually found things that are quite poetic, that we say, like neurons fire and synapses spark. It naturally made guessed that the workshop would be a lot about physics and thermodynamics. So impressive. However, obviously, AI has problems. And one of the big problems of AI is energy. And actually, I found these tweets. Somebody asked Sam Altman, so the CEO of OpenAI, if this AI is going to remain free forever, and his answer is no, because the compute costs are eye-watering. So eye-watering is not very scientific number, so here is just a little of guesswork. ChatGPT is a really big model. As a matter of fact, it does not even fit. So normally AI are operated on graphics cards, GPUs, but ChatGPT won't even fit on one GPU. You actually need 8 GPUs, and not the GPUs that you would have on your PlayStation, but really the upscale Tesla GPUs that cost more than $10,000. And so a server with 8, so yeah, when you ask a question to ChatGPT, 8 GPUs are computing stuff. And so a server like that would be something like 4,000 watts. It took 10 seconds to write a poem, so that means the energy consumption order of magnitude would be something like 10 watt hours. Not that much, actually, but very significant. And if you have 1 million people using this, that ends up being a lot of energy. And I always like to compare with brain. So if you imagine a poet, I think writing a poem like that would actually be quite easy. I mean, yeah, it doesn't even rhyme. It's like spontaneous writing. So I imagine a poet would take something like 2 minutes. Power consumption of the brain is something like 20 watts. So you get an energy consumption of 0.7 watt hours. So I think both of these numbers are unfair, because actually the server would probably be able to produce several sentences at the same time, and same, actually, only a fraction of the brain of the poet is really writing the poem. A lot of the brain is doing other tasks, like, for example, vision. But that gives an idea. And we see that even on a task like that, brain seems to remain more energy efficient than computer. But I have to say that I've been making this type of comparison for years, and until recently, the gap was enormous. And now you see different, but not that different. Still, for application, as Sam Altman was saying, this type of number is very problematic. It's a very big cost for the industry, which has to pay this electricity, and it's possibly a very big cost for the planet if language model become used all over the place. And that's really inference. You have another energy cost, which is also to create the model. So that's training the model. And here, OpenAI actually did not release any number, but Google, a few months ago, released the Google Palm language model, which is quite similar. And they actually disclosed they use 3.5 gigawatt hour of electricity to train this model. And that's only the final run. I mean, before that, there was a lot of research that probably failed before they were able to produce really good model. 3.5 gigawatt hour of electricity is 20,000 years of brain operation. Obviously, we are able to learn language in less time, only a few years. And so that showed that on training, brain is really particularly energy efficient, way more than artificial intelligence. In terms of application, both training and use, or what we call inference, matter. Because obviously, this number, 3.5 gigawatt hours, is way more than the 10 watt hours that I was here. But the idea is that once you have tried the model, you are going to use it a lot. So this ends up being very important. And depending on the application, really over the lifetime of a model, the dominant energy consumption might be either training or inference, but it seems that in general, it's actually rather inference. By the way, I forgot to say that these two images were actually produced by an AI as well, where I don't have copyright issue. So anyway, this was a little the context of what of my presentation. So now I'm going to say what I believe are lessons of the brain to do energy efficient intelligence. And then I'm going to show how these lessons inspire our research, which is to do dedicated electronic circuits for artificial intelligence following brain principles using a new technology that is called memristors. So I'm going to show two circuits that we made with memristors to do inference. And then I'm going to show an approach where you will use memristors for learning, actually using their imperfection. So yeah, that's the plan for my presentation. So let's go. So I think here it's very clear. Modern AI usually, I mean, like the one I just showed, built around artificial neural networks. Artificial neural networks are actually very different from the brain, but they do have some similarity, like the fact that they rely on neurons and synapses. But in artificial neural networks, what is, I find really interesting, is that the mathematical operations are really not that complicated. If you look at the equation from a neuron, it's really a weighted sum, so basically an ensemble of sum and products of neural and synapse values. And then you apply a nonlinear function, but in artificial neural networks, this nonlinear function is usually extremely simple. So we have a situation which is quite special, is that the mathematical equations of a neural network are not really complicated, especially when you do just inference, but you do have a lot of parameters. As a matter of fact, for example, the ChatGPT I was mentioning before has 175 billion parameters. So in terms of electronics, that means that when you perform AI, actually you don't do that much arithmetics, but you need a lot of memory access to load and store all these parameters. And turn out, for computer, this is not a very ideal situation. And in fact, memory access in a computer is something that is very costly. So here I show people actually not usually realize that, but they don't necessarily realize to what extent it is true. So these are some numbers that come from a beautiful paper from Shahar, who actually I think is in the room, that illustrate this. So this data on a modern computer, and it compares the energy it takes to add two integers with the energy it takes to access them from memory. And this is the energy it takes to access them from memory. These integers are stored in the cache of a computer. So that means on the, because you know, in a microprocessor, you always have a little memory that is on the chip of the microprocessor, which is called the cache memory. And so it takes actually 60 times more energy to access the data than to do an arithmetic operation on it. And here is the number if the integers were actually stored in the main memory of the computer. So really in the DRAM, which is a separate chip from the microprocessor itself. And you see if you need to access the main memory, the energy cost is really tremendous. And when you do a neural network that can have billions of parameters, you need to access the main memory a lot. So you can guess from this table that when you actually do AI, because we don't have that much arithmetics, but a lot of memory access, almost all the energy will actually be for accessing memory and in general moving data around. That's not very satisfactory. And my impression is that actually in the brain is quite different. In the brain, you don't need to spend that much memory to access stored data, and probably most of your energy consumption will really be used for doing useful stuff. And the difference is, of course, that in the brain functions with real neurons and synapses, and so it's not like the value of the neurons and the synapses is stored on one side of the brain, and the part of the brain that can actually do neurons equations is somewhere else. The neurons and synapses are exactly right there, right where the computation is done. And so accessing parameter value is actually not costly because they are physically where you need them. And so something also I always say to electrical engineers is that, I mean, in the brain, I mean, usually we believe the long-term memory is really stored in the synapses, and the brain really has a lot of synapses. It has actually has 10, for the human brain, 10,000 times more synapses than neurons. So what I say about electrical engineering people is that, to me, the brain is really like some kind of gigantic memory where you have computation that has been scattered all around. And because the computing really happens in the memory and not in a separate computation unit, the brain saves a lot of energy with regards to yeah, sorry about that, with regards to a computer or graphics card. And so that's something we want to imitate. Another striking difference between the brain and computers is that brain computes mostly in an analog fashion based on low power, slow, noisy, and variable nano devices. So personally, when I see the current as a function of time in an ion channel, I'm very horrified by how noisy it is. Same synapses look vastly unreliable. I mean, I have seen reports that synapses might actually fail transmitting a lot of the spikes, sometimes as high as 10 or 20% of the spike. And despite, and then, you know, the computation in the neuron really happens in an analog form using the membrane voltage, which is, by the standards of electronics, quite noisy. So you have basic operations that are actually very approximate. But then, by combining all these approximate operations together, brain managed to be very intelligent. And that's very different from computer. Because in computer, we compute with floating point arithmetic, which is either 64 bits usually in computers or 32 bits in GPUs. And that's very accurate. So no matter what we do in the computer, we use very accurate arithmetics. And obviously, this has a cost. I mean, all this accuracy. But what is a little surprising is that normally we really need this precision. I'm sure many of you have done scientific computing. I mean, even using these floating point arithmetics, we do have rounding errors problems. So it's a little mysterious why, even with this high precision, sometimes we struggle, and the brain is able to be intelligent with very approximate computation. But actually, we have understood that AI is special. In the landscape of computing, AI does not necessarily need precise arithmetic either. So this is one of the first papers that really realized that. So they train a neural network to recognize images, and so then they first use it with floating point computation, and you see the error in this situation is 7%. But then they made approximate version of the neural network using 16-bit, 8-bit, or 4-bit integer computation. So we look at the diagonal where all the computations are made in 16, 8, and 4 bits. And you can see that with 16 or 8-bit precision, the error rate is just the same. And if you use 4-bit integer computation, which is really very, 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 very imprecise, the error goes up, but to 8%. It's not that bad. I mean, it still works, although you do the arithmetic that is so much simpler. So it seems that this concept of using approximate computing by the brain can actually be used for AI as well. And so based on these two things, we get really two lessons if we want to make more energy efficient AI, which is to bring the logic and the memory closer and to compute less precisely. And maybe 10 years ago, when we were saying this as academic researchers, I mean, we sounded very crazy. But now this idea has been very accepted. And actually, the industry is already designing systems based on these ideas. So this, for example, the Google TPU, it's a dedicated computer, especially for AI, that to a large extent functions using these concepts. I mean, the way it deals with memory is special. It's really dedicated for AI, and also it computes with 18 or 16-bit accuracy, a lot less than what we normally use. And as a matter of fact, all these software companies now develop computers, their own computers, and when you use AI services, very often it's not really on a normal computer, but on one of these dedicated computers. So now, as academic researcher, we want to go even further. Not only bring logic and memory closer, but really try to merge them we totally associate them in the same way as the brain does. And same, instead of just computing less precisely, we want to really compute, maybe in a more analog way, using device physics in a way a little similar to the brain seems to be using the biophysics of its devices. So at the end of my long first introduction section, so now I'm going to go on toward our actual work. So if we want to make this type of new AI, which we can call neuromorphic, we really need to have something that is really like the brain. We need to have some artificial neurons and some artificial synapses and to connect them. Neurons, as a matter of fact, we know we can do AI with neurons that are not that complicated. I mean, complicated neurons like the brain actually have really interesting benefits, but they are not necessarily needed. We can already do great stuff with simple neurons. So actually fabricating neurons with conventional electronics technology is very feasible. Synapses is another story. Synapses connect neurons, but they should have memory as well. And memory, we are going to see, is a big problem. So if we want to do this type of neuromorphic circuit, we really need to care about synapses. And the reason why doing synapses in normal electronics technology is hard is memory. Because in fact, the normal electronics technology is transistor, so that's the schematic for, that's the symbol for a transistor. And doing memory with transistor is hard. So this is actually the simplest circuit you can do, which is called a static RAM. So that's the type of memory that makes the cache of microprocessors. And you can see to do only one bit of memory, you need 6 transistors, and they are connected in a quite weird way. So actually this circuit ends up being big. And because this circuit is big, you cannot actually make a lot. And so that's why, for example, in a microprocessor, you don't have a lot of memory, and you need a main memory which is fabricated in a different technology and which is put in another chip, and which costs so much to access energetically. So that means that if we want to make these artificial neural networks neuromorphic, and they are made only with MOSFETs, we cannot have a lot of synapses on chip, and if we cannot have a lot of synapses on chip, that's a very severe limitation. But fortunately, we have new technologies that are emerging. And one of these new technologies is called memory store. So actually, in general, academic world, we tend to call them memory store. The industry tends to call them resistive random access memory, but that's really the same thing. And these new memories are nano devices that are placed on top of the transistors. So you can see here an image of the technology of our partners at Leti. So this is seen from the top, and this is a side cut. So the transistor is here. On top of the transistor, you have wires that connect the transistor. And here on top, you can see you have this memory store, which is fabricated in hafnium oxide. So just above the transistor. So it's same chip. It's fully integrated with MOSFETs. You do not need a separate chip. And here is a cartoon of the device. So you can see you have 2 electrodes, and between the 2 electrodes, you have the resistive switching material, which is here hafnium oxide. And the idea of hafnium, of this memory store, is that to make a really stable hafnium oxide, what you would normally do is to have 2 atoms of oxygen for 1 atom of hafnium. But here we intentionally do not do that, and we don't have enough oxygen. Because if we do that, the material is actually full of defects. And then what happens is that these defects are actually mobile. So when you apply a very high voltage between the 2 electrodes, you are going to be able to drive electrochemical reactions. And these electrochemical reactions are going to move atoms in the device and create this type of filaments that connect, so these are filaments of defects that connect the top electrode and the bottom electrode. And when you have a filament between the top electrode and the bottom electrode, these filaments actually conduct electricity. So the electrical resistance of the device is going to drop. And then, if you apply a voltage in the other direction, an opposite voltage, you can actually generate electrochemical reaction in the other direction. And you can actually dissolve the filaments. And when you have dissolved the filaments, the memory store is going to go back to a high electrical resistance. So, yeah, it's really a nano device, and you can change its electrical resistance. So it doesn't sound very normal that by just applying a voltage, you can move atoms in a device, but you have to remember that a nano device, this is only 5 nanometers peak. So if I apply 2 volts between the 2 electrodes, it's actually a very high electric field that is here. And this very high electric field is enough to move atoms. So that's how memory store work. If you apply high voltage, you can move atoms and switch the device between low and high resistance. But on the other hand, if you apply a low voltage, then it will be not sufficient to move atoms, so the device is going to remain the way it is, and so you can use these lower voltages to read the resistance. So it's really a memory, except that the memory state of the device is the electrical resistance. You program it to high resistance or low resistance. So probably you see where I'm going, because this device kind of looks like a synapse. You have a device that has 2 electrodes, and it can be either conduct electricity well or not conduct electricity well. Said otherwise, it can conduct information well or not conduct information well. So it's a little like a synapse that can transmit or not transmit information well, depending on synaptic weight. And indeed, the whole community is very excited about using these devices as artificial synapses. And this is actually even better than it sounds. Because let's look at what happens when you have a matrix of memory stores. So you can see here in my cartoon, I have horizontal wires, I have vertical wires. At that intersection of horizontal and vertical wires, I have a memory store. So let's imagine I apply here for each horizontal wire voltage S1, S2, S3, etc. Then each memory store, you see this memory store is going to see a voltage S1. So then, due to Ohm's law, the current that goes in this memory store is going to be S1 divided by the resistance of the memory store. And here I'm rather going to focus on the inverse of the resistance, which is called conductance, and that I'm actually going to call W, and which is expressed in Siemens. So the current that flows in this memory store is W of the memory store multiplied by S1. And then you have all these currents that go on this vertical wire. So due to Kirchhoff current law, this current thumb, and so the current that flows here is given by this equation. And here actually you recognize this equation that is exactly the equation of a neuron in an artificial neural network. So you see, when you make a matrix of memory store, they will naturally implement the equation of a neural network without you to have to do anything, actually. You don't have a circuit that calculates the product and the sum. This happens naturally, really due to the physics of the circuit. And it happens right where the memory is. So if you remember my table where we see this very high cost of memory access, all this is going to disappear because computation happens right in memory. So yeah, we've been, as a community, extremely excited about this prospect for a long time to reduce energy consumption of AI. And it's taken a while, but now we can really do it. So here is, for example, a circuit that we designed and fabricated with our partners in Marseille and at Leti in Grenoble. So this is really a fabricated circuit. So you can see this is a picture of the circuit where we added some colors. And here is electron microscopy image where you can really see the middle connection where the memory stores are. And so we made small circuits like this that are 32 by 32. So that's 124 1024 memory stores per array, and we programmed neural networks on these memory stores, neural networks that are able to classify arrhythmia. So the input is really ECG heart measurement, and the output should tell you if the heartbeat is normal or if it has arrhythmia, and if it has arrhythmia, what kind of arrhythmia. So we programmed neural networks, and we found that it was able to recognize arrhythmia 95% of the time. So we were really excited about it. Unfortunately, we also saw something not that nice, is that after we program our memory stores, we tested it worked very well, but if we test it a few hours later, it actually didn't work as well. Like, you can see in 15 hours, the accuracy has reduced to 87%, and in this bad one, it has even reduced to 77%. So it seems like the memory stores were not as stable as we hoped they would be. And indeed, when we look into the details at the conductance of the memory store, you can see, so that the conductance measure as a function of time, you can see, so it's a little messy to see, but if you look in detail, you will see that many memory stores are actually very stable, but some of them are not stable. Like, for example, if you look at the dark blue one, boom, this one drops. Especially when you go to lower conductance, you see a lot more instability. And this unstable memory store caused our accuracy to drop. So we found a way to program the memory store that would be more reliable, and it's very simple actually. The idea is that we program memory stores, and then we wait for a while, like I think 5 seconds in the paper, and after 5 seconds, we check if the resistance has moved. And if the resistance has moved already, it means that the memory store is not stable, so we try again. And we try again until we have managed to program the memory store in a really stable state. Because yeah, as with these memory stores, I told you when you program that, what you do is you create these filaments of defects. These filaments are sometimes very stable and sometimes not that stable. And it's very hard to control. So the best way is just to try again until you have found, you have managed to create very stable filament. And if it's stable after a few seconds, in fact, in general, it's stable for months. So if you manage to program memory store and it doesn't change after 5 seconds, we don't do anything. And when we did that, we actually were able to program our neural networks way more stable. So in blue is the measurement I showed before, and in black is measurements using the same circuits, but now programmed with the weight. And you can see that it started at 95%, and 2 months later, so basically we just put the circuits in a box and measure them again 2 months later, the accuracy was still 95%. So yeah, so this beautiful concept works. However, I have to say, it's still a challenge. And the circuit I showed you is an academic circuit with 32 by 32 memory store. For very big application, we need to scale up. And scaling up is not easy because electronics, unfortunately, is not easy. So scaling up really hard the system is something that is a little out of reach for my group because we are academic, but not out of reach for industry. So for example, TSMC has been trying to scale up these things very hard. And for example, they have this 2 megabit computing memory array that computes based on the principle I showed before. But problem is that when you make really big circuits, things become complicated. And you have all kind of small effects that like offset, variability, all the tiny parasitics, all kind of electronics problems that become really significant when you scale up. And so that's the schematic of what they actually did. And you see you have all these things that are compensation, all kind of things to fix the problems you have when you scale up the approach. So it ends up being a very complicated circuit, but it works. However, if you look at it, you will realize they don't do what we did in our work before, which is to really program the memory store in an analog fashion. We really use memory store to program real weight. And that goes, we had the stability issues, and we need to find a solution for the stability issues. Here, when they scaled up the approach, they actually only use the memory store to store the binary values. That means they either program the memory store to the lowest or to the highest resistance. And that makes things a lot easier in terms of stability and in terms of electronics. So very often in electronics, it's like that. You have beautiful concept, but when you apply in practice, you need also to do some compromise, and something that is beautiful conceptually might have a hard cost. So I actually believe the analog concept is going to scale, but still a lot of still some research here. It's still in development. And now I'm going to show you another line of research for us, which actually does not concern neural networks, because we don't do only neural networks. We know neural networks excel at big data situations where you really have a lot of training data. But that's not always the case. And there are many situations, particularly medical applications, where you don't have that much data, and then neural networks do not work that well because they tend to overfit the examples you give. And there it's really important to bring expert knowledge to compensate for this. An approach that can make really good sense in that situation is more Bayesian type of approaches. So Bayesian approaches are based on Bayes' law, which, for example, for a medical task, the probability to have a disease given some observations by some sensors, for example, reduces to the probability of seeing these observations when we have the disease, which is way easier to get, multiplied by a prior. And this thing is constructed heavily with expert knowledge and can be quite hard to compute. And that's where you have all the expertise of Bayesian modeler to create this type of models for the likelihood. Bayesian reasoning, it puts a lot of focus on expert knowledge. It's not something that is directly brain-inspired. However, there are signs that the brain might be using Bayesian reasoning, and actually many researchers in Paris are working on that. A simple illustration of this is the optical illusions, because the optical illusions, they show us that what we see, what we perceive, is actually heavily influenced, is not necessarily directly the physical reality, but is heavily influenced by prior. So for example, in this famous illusion, physically, in terms of pixel color, A and B are really the same color. But because there is a shadow, and we have this prior knowledge that shadows make things darker, our brain actually compensates that a little, and for us, the color here appears lighter than here. And people always complain about prior that they are very subjective, and what's very interesting is that the priors used by the brain seem to be subjective as well. You probably remember, this internet phenomenon a few years ago, this dress that personally I see white and gold, which is the actual color of the pixel of the image, but apparently people who grew up in sunny countries, their brain actually is able to compensate, to use some prior to correct the image, and they actually see this image with the real color of the dress, which is in fact blue and black. So, and apparently they see it blue and black as clearly as I see it white and gold, which I actually find very hard to believe. But anyway, so we actually fabricated a circuit with memory stores to do Bayesian inference in a way that associates logic and memory tightly. So this is a photograph of our circuit. So this is a piece of silicon that's 2 millimeters by 2 millimeters. And the tiny squares you see here is where the memory stores are. So we can zoom here, and you can see here the memory store array, and this is the electron microscopy picture where you see where the memory store is. So this was our first circuit that really associates memory store and logic this way with multiple arrays of memory stores. So you can see our arrays of memory stores are quite small. We have newer circuits now with much bigger arrays of memory stores. And this functions with a very unconventional computing concept, which is called stochastic computing. And the idea of stochastic computing is that to code for a real number, you use actually one wire. So in a way, it's kind of similar to the brain, because in the brain, a wire with spikes can code for a real number. But it's also quite different. The idea is that in stochastic computing, a wire is it will be what we call a stochastic bit stream. So, for example, you can see that in this wire, you have a succession of numbers 0, 1, 1, 0, 1, 1, and half of the number are ones. So this wire is going to code for the value 0.5, proportion of 1/2. This one actually has more ones than 0, and so it will code for the value 2/3. No, it's actually 6 over 8. So 3/4. And yes, that's the way things are coded. So the probability, so you can see that in this wire, the probability to have 1 is 4/8, and the probability for this one to have a 1 is 6/8. So that seems like a weird way to code information, but what's nice about it is that arithmetic operations become very easy. So for example, if you put an AND gate between two wires in stochastic computing, you get on the resulting wire, the probability to be 1 is actually the product of the probability to be 1 on the first two wires. So that means that in stochastic computing, a simple AND gate, which is a very, very, very simple circuit, actually is enough to multiply real number. And in normal electronics, a circuit to multiply real number is actually a really big circuit that has a very high energy consumption. So yes, simple AND gate implements two probabilities, and it has some resemblance with neurons, but just some resemblance. I mean, I don't think neurons actually do that. So that's our circuit. So yes, I was telling you, here you have the tiny memory store array, and you can see all around the memory store arrays you have digital circuits, and in between the memory store arrays you have some more analog circuits that make the connection between the world of the memory stores and the world of the digital, and that can be used to read or write the memory store values. And what does it do exactly? So the idea is that, in fact, in the memory store, we stored likelihood values, and we have circuits all around the memory store that can read the likelihood values and generate random bits based on the value of a likelihood. And when you have these random bits, that's good enough to do stochastic computing. And so we have an AND gate, which is close to each memory store array, that's going to AND the stochastic bit that comes from the memory with the stochastic bit that comes from the previous memory array. And so each of these blocks generates random bits, and they get multiplied, and then they get passed to the next array. And so that will very naturally implement Bayes' law for a very specific model, which is called a naive Bayes model, which I have written the equation here, but the architecture can actually be made more complicated for non-naive, more sophisticated Bayes equation. The details are in our paper. But it's also a very conceptual thing, because it's really this idea that we have the computation that happens really right next to the memory. So it's not really in-memory computing, it's more near-memory computing. No computations happens really in the memory, but all the computation fits near the memory. And where was I going? And between the different memory blocks, you only pass the single bits because it's stochastic computing. And in fact, when you look in the details, you realize that most of the times these bins are really zero. And so actually it's very little information that get passed between the memory arrays. And so this thing ends up being extremely energy efficient. So these are measurements on our fabricated circuits. So this is before we program the memory store. So the likelihoods are very random. And after programming, this is what we actually program in it. It looks funny, but it actually allows us to test the chip well. And you can see that in this project, we actually use memory store in a binary fashion. It's really not as advantageous to use them in an analog. When you do neural network, it's very advantageous to use memory stores in analog fashion, but for Bayesian inference, it's really not that advantageous. And so the likelihood are stored as 8-bit integers in the memory. And these are measurements for actual inference. So the x-axis is what you expect from Bayes' law, and the y-axis is the probability you actually get from the chip. And here is something important about stochastic computing. Stochastic computing relies on real numbers, but random numbers. But random numbers are actually hard to generate in electronics. So we use actually fake random numbers, or pseudo-random numbers, that can be generated at very low energy cost in electronics. But pseudo-random numbers are not really random, so they have a seed to be initiated. And you can see that when we use random seed, I mean, the measure on the result of the chip, they follow Bayes' law, but not perfectly. That's because they are not really random numbers, and the seed choice are not equivalent. On the other hand, there is one particular seed choice that you can always use, and that always gives great results. So, and that's what is in these measurements. And you can see when we use this optimal round seed choice, the measurements follow the Bayes' law very precisely. We are very happy about that. You can see my graph has different colors, and these different colors correspond to measurements that are made with very different supply voltage, ranging from 0.4 volt to 1.2 volts. To be clear, electronic circuits consume more energy when you use higher voltage. So lower voltage is better in terms of energy. And you can see that we can actually reduce the supply voltage, and the circuit still works until we see these points, which are around 0.6 volt supply voltage, where you start to have errors. And it's only possible actually because we use a memory store in a binary way. Because we use memory store in binary way, our circuits are extremely robust, and you can change the supply voltage and it still works. The other circuit where we use memory store in analog way, everything needs to be super tuned. And this would not be, this is not possible in the analog circuit. So that's yet another example that if you want to do brain inspiration, doing things analog makes sense. However, it does bring a lot of challenges in terms of electronics, and doing things binary actually also has a lot of advantages. So it's still very much research. In our paper, we also designed, not fabricated, a much bigger Bayesian machine, so the same concept but scaled up. And this scaled up version, we can train it to perform gesture recognition, a real application, and that allows us to really evaluate the energy efficiency of the whole thing. So because it's stochastic computing, you can kind of tune the accuracy of your AI based on how long you look at your stochastic computation. And so we can plot this type of graphs of energy efficiency, energy consumption as a function of accuracy using different schemes of stochastic computing. So one is power conversion, one is conventional, in our paper. But you see that basically to reach something like 85–90% accuracy, we need something like nanojoules. As a comparison, a more standard electronics approach, which is to use microcontroller unit fabricated in similar technology, would use 2 microjoules. So that gives you an idea of how beneficial this type of approaches can be. No, sorry. Okay, so I've been a little longer than I thought I would, so I'm going to go very quickly on this last part and just give the big picture. Anyway, I think I covered what I really wanted to say. So everything I showed until here was about inference. These are AIs that are pre-programmed to the memory stores. But it would be really hard to be able to train the AI on the memory store as well. And that's something that is actually extremely hard to do. Because, so when you train an AI, you need to adjust the values of the parameters very progressively. And because memory stores, they function, with these filaments, that's actually, I told you they can be unstable. Programming them is actually in a very precise way, is very hard. And it forced to, doing learning with memory store is really, really hard. However, there is one very specific type of learning, which is the Metropolis Hastings Markov chain Monte Carlo, where learning happens based on random numbers. And the idea of MCMC is that, when you have a parameter has one value, and when you do training, you need to generate a new value, which is actually a random number based on the previous value. The new value needs to be drawn from a normal law. And actually, when you program a memory store, so here are measurements where we program a memory store many times. And you can see that the conductance of the memory store actually follows a normal law. And we know the details of the normal law from the physics of the memory store. So in MCMC is a type of learning where you need to program the parameters random way using normal law. And memory stores, actually, when you program them, it follows normal law based on the current that you use to program them. So what's the idea? Actually, so this big imperfection of memory stores, the fact that when you program, you never know exactly what conductance are going to have, we can actually use it to do MCMC. And this way, we were actually able to do learning with memory stores. So the details are in our paper, but the idea is really simple. The idea that basically we have rows, we have a big array of memory stores, and the parameters are in the memory stores, and each row is an implementation of the model. And to get the next model, what we do is that we take the current that flow in the memory store, and we bring it back to the next memory store, and that's going to program the memory store to a new value, which is a random value based on the current of the previous memory store. And that really just naturally implements MCMC. And we did it for real, and we trained an array of 15,000 memory stores to recognize images of cancerous mammography. And it actually worked really well. So, for example, these are the results of our experiment. So this is an array of 16 by 256 memory stores. Our model is very simple. It has only 16 parameters. And we created 256 value of the model. And so here, what is plotted is the accuracy of each of these models to recognize cancerous imaging. So the first ones are really bad. And then you have a collection of models. Some are really good, some are worse. But what we do is that we look at all of them, and you make some kind of majority vote to decide if the image is cancerous or not. And then we're actually able to recognize cancerous images with an accuracy of 98%, which actually match exactly what simulation predicted it could be. It's actually as high as what a computer can do on this particular task. This never happens. We were really happy. Usually experiments with memory stores are way worse than simulation. And once again, this is very energy efficient. I mean, learning requires 6 microjoules. whereas it would have taken 600 millijoules on the computer, which is still a small number, because to be fair, this is a very easy task. So learning is really very, 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 very hard problem. So here, I mean, this cancerous task sounds, it's really not that hard task. And going to be able to learn ChatGPT with memory store, so much research is needed. But my impression is that if we are going to be successful to do learning with memory stores, we really need to take into account how memory stores really are. Because memory store cannot do very precise things, but yeah, you can see that for learning, conventional learning of deep neural network is with very precise computation, but some approaches actually are not like that. And so maybe taking inspiration from these approaches, and particularly approaches that come from neuroscience, can be the right way to achieve to do really energy efficient learning using memory stores. So I went very quickly on that because, we covered so many things already, but yeah, all details are here and feel free to contact me. So anyway, this allows me to conclude my talk, so I wanted to insist why I believe computing like the brain, or to some extent inspired by brain principle, can be really useful. So really challenge that we have in electronics with this memory store is device imperfection. I do believe the brain has the same challenge. So, and I do notice AI tend to have some tolerance, but for some things, like for example, inference is very tolerant, training is not. I quickly mentioned this idea that the statistics of device can even be exploited in this context. But yeah, the next challenge I mentioned will really be about scaling and learning. And yeah, I think I covered everything. I thank you for your attention.
Okay, so are there any questions to the speaker? Yeah, so Damien, maybe I can start with the question. Can you hear me?
Yes, I hear you.
Yeah, you gave at several spots in your talk some energetic cost for learning. For instance, you just did it a couple of slides ago, learning for one memory store compared to normal computers. Yes, exactly that one. I just want to understand these numbers. How do you compute? Because for memory store, what is the number you are giving here? Are you also taking into account, because I guess you do some learning on a real, on a normal computer on the side. For instance, when you do your MCMC learning, right? You have to estimate these probabilities of accepting or rejecting the moves. And that you do that on a conventional computer.
Yes, so I went a little quickly about our work. So our work is semi-experimental. That means that everything involving the memory store is done experimentally, and all the rest is done on the computer. So that means that we just cannot measure the energy consumption to do learning, because it doesn't make sense, because so much is done on the computer. Yes. So this value of 6 microjoules is an estimation, and this estimation is based on the design of a system that would do everything. But this system that does everything, we did not fabricate it. We only designed and estimated its energy consumption. So you're absolutely right that especially once you use memory store, the cost of accepting the model is really dominant. So what we did is we found really approximate ways to do the acceptance, like largely simplified equations that actually still worked for this task and consumed a lot of energy. And so these 6 microjoules is based on simplified equations for the acceptance. I have to say that I don't know if our simplified equations would work on much more difficult tasks than the one we train in the paper. So if we wanted to scale this, the energy cost of accepting the model might become dominant. But to be fair, MCMC only works for small models anyway.
Okay, thank you. Is there any other question? Yes, Alice? Okay, maybe I can. Yeah, if you come here and.
Hello, Damien. When you do your thing where you program the memory store and you try to see if they are stable for 5 seconds, and when they will be good for months, what is the reason for that? Is that you move kind of different types of defects and some are good and some are bad, and you stumble on a good one, or what's the mechanism?
So to be totally fair, so that's actually the challenge about memory stores, and especially this particular type of memory store that function with filaments of defects. Mechanism is not clear. And in that particular case, we don't know. But one thing what is for sure is that so when you program the memory store, you don't control the shape of the memory store. And the shape of the filament, and it's likely that sometimes, you generate a filament that is stronger or which is further from really structural defect in the memory store, and that ends up being more stable. Because also a lot of this noise is due, for example, to random telegraph noise, which is very sensitive to other type of defects in the material. So if your material is further from them, that would be less sensitive. So yes, so when you program memory store, sometimes the filament is more or less stable, and it's not that clear. Something I also have to say about you have to be a little careful in the literature is that this problem has been a little underestimated in the past. So there are many papers that actually will only report this value. So be careful about that. But in modern paper, usually people pay a lot more attention to the retention.
Okay, thank you.
Okay, any other question?
Yeah, one question to that as well. On the next slide, you showed the...
Can you go to the next slide, Damien?
Yes?
Yes, the accuracy improves after some time. Do you have an idea of what's happening there? So even after 2 months, it's higher than the initial accuracy?
Yeah, you mean on the black curves?
Yes.
So on the black curves, you see an increase of accuracy right at the beginning. You see after a few hours, maybe, which seems to remain stable over 2 months. So you understand why you may have an increase like that?
Yes. So I skipped some details about the work, but in the early life of our device, there is a little of broadening of the conductance of the memory source, and our training technique actually anticipates that. It already anticipates our memory store. So our neural network is trained based on how the memory stores are going to be a few hours after having been programmed, and so that's why it increases a little at the beginning. This thing, I think, is quite particular to our technology, so I'm not sure it's true of all memory stores.
Okay, thank you. Any other question? No, okay, so thank you very much, Damien. Okay.
Yes, thank you.
Bye-bye.